Okay, thank you. So we're going to do functions of a single variable, but you did that already. You did that in Algebra and Calc 1. And let me do a function machine for that. So I like doing these function machines. So a function machine for a function of a single variable, you know, like y equals f of x, for example, like y equals x squared, you feed it x, which is a real number, and then the output is y, which is also a real number. And you did all that. In Calc 1, you learned how to do derivatives and integrals of that, as well as Calc 2. Okay, what's another function we've studied here in Calc 3 already that we just completed in the previous chapter? Well, vector valued functions. That's a new kind of function you learned here. And we did all kinds of things on that. We discussed what the graphs look like, the domains, taking limits, differentiating, integrating, as well as applications. The function machine for vector valued functions has this look to it. You've got your notation for your vector valued function. Here we'll do a 3D one. It's a vector, and what you feed it is t, the parameter, which is a real number, like, you know, 2 seconds or -5 seconds or whatever. And then the output is what? Does anybody remember what the output is for a vector valued function? I'll give you some choices. Is it a real number, a point, or a vector?
A point?
A vector?
Oh, vector.
It's actually a vector, but when you graph it, you only look at the collection of the tips of the vector. And so you connect the dots or the points when you graph it. But actually the output is a vector. Okay, so in this case, it'd be some constant vector ABC for some real number input t. Okay, now we're going to introduce a brand new function today. Yeah, functions of more than one variable. Might be 2, might be 3, might be 4, might be 10. Well, how many? Well, we won't go too crazy yet, but I claim you already studied this. You just didn't know it. Some people didn't tell you that you did already study functions of more than one variable. And you may be thinking right now, really? I don't remember. Sure. Take a look at the work formula that we did about a month ago. You know that work is equal to force times distance, right? Well, this is actually a function of two variables, force and distance. How about the volume of a right circular cylinder? Here's a right circular cylinder right here. You've got its height and you've got the radius of its base, and the volume is pi r squared h. That's a function of two variables because it's a function of the radius and the height, r and h. And you've done functions of three variables. For example, if you were going to, pardon me, no, I don't have COVID, don't worry. If you had a rectangular box with some width, some length, and some height, you know the volume is equal to the product of the width, the length, and height. So the volume is actually a function of three variables. Oh, now let's look at notation, though. You probably haven't seen notation for function of more than one variable. So here we go. Notation. If you have a function of two variables only, say you're calling the function z equals f, and in parentheses here, instead of just f of x, you're going to have f of whatever your variables are delimited by commas. So x comma y. And this is just an example of a function of two variables, x squared plus xy. Okay. What about a function of three variables? You can have that. So they're just naming this function w, where the three variables are x, y, and z. And so notice the notation. You have f, and then in parentheses here, you have your three variables delimited by commas. And this could be some example of a function of three variables. Now, folks, these particular functions are written in what we call explicit form. So what do you mean? Well, explicit form, let's just do a quick review from, say, Calc 1. Do you remember that when you had you had something called implicit differentiation? Does anybody remember implicit differentiation? You probably tried to forget it. Well, it's coming back soon, not today, but I do want to remind you that if you have a function written like this, y equals x squared plus 3x minus 1, that's written as an explicit function. It's an explicit function of x. But if they rearranged it where they have all the junk on one side, let's say I subtracted y from both sides of the equation, this is written in implicit form. Okay, it's not solved for y. And there are many implicit functions that are a lot crazier than that, where you couldn't even get them into explicit form. So here's another implicit example, say from Calc 1. Sine of xy minus y cubed is equal to e to the x, I'm just making something up, plus arctan of x plus y. That looks pretty nasty. But there's no way you could even write that in explicit form, because how would you solve it for y? But it would have a nice graph, and you could still talk about slopes of tangent lines. And that's why in Calc 1 they made you learn the technique of implicit differentiation, so you could get the dy dx and get, you know, the slope of the tangent line to that curve, even though it was given to you in implicit form. We have the same idea here in Calc 3. The same idea. You could have an explicit function like this, or if you rewrite it where you get everything on one side, you know, where it's not solved for z, say, that would be the implicit format for it. But you could have really nasty implicit functions of x and y, where there's no way, even if you were, you know, 2 PhDs in math, you couldn't solve it for z. I'll just do an example here, you know, like sine of xyz equals x plus 2y plus 3z. That would be implicit, in implicit form, okay? So typically you're going to get your functions, if you're lucky though, as explicit format, z equals f of xy, for example. But if they wanted to give it to you implicitly, where they moved everything over to one side and got 0 on the other, you might be asked to deal with this function of 3 variables now, the junk that's got x's and y's in it, and then this third variable z, and this is known as implicit format. So what I'd like to do now, just briefly, just to have fun here, is show you sort of the difference between explicit and implicit. So this, no, I don't want to graph anything here. So if I just do, you know, this is a nice grapher where I can graph, you know, explicit functions of x, okay, fine. But I can also graph, you know, implicit functions of x. So if I went, and you can't do this calculator because your calculator is kind of grouchy when it comes to, I'm having trouble with my thing here. So I could just go, you know, plus 2, I have no idea what I'm graphing. I'll just put 3. What does that even look like? Oh, okay, there we go. That's kind of an interesting graph, all right. But you can do this in 3D also. So that equation that they did for us, just at, you know, z equals, what was it, x squared plus xy. I don't know. I'm not sure what this is going to look like. Ooh, that's a nice surface. See that? It's kind of pretty, actually. And this particular graphing software is cool because if you are given an explicit function, it lets you choose not only different colors, but it gives you rainbow choices and candy stripes. Woo, that's kind of fun. Wow, that's really pretty. And what else do I get if I have explicit? Candy bars. Nice. Okay, fine. But the if I want to, I can come up with an implicit function of x and y where I couldn't solve for z even if I, you know, was a smart rat there. So sine, let me do a real interesting one. Let's just see what this looks like. I'm not sure. Equals x plus 2y plus 3z. Let's take a look at that. Oh, wow. So that one is the one that's kind of purple. This one doesn't allow you as many color choices when you do implicit. But what's really cool, let me get rid of some of these, is if you have let me do this. Let's do one from your Calc 1 days. If you had an implicit function of x and y back from Calculus 1, that's kind of a cool looking implicit function that you could have been asked in Calc 1, like they could have given you a point like right there and then draw a tangent line to that point and then come up with the equation. But what's really cool about this software that I have here is I can put an inequality symbol in there. Well, I can. Nope, I gotta retype it. Yeah, that's too bad. Let's try this. Sine of xy less than. Nope, I have to type it from scratch. Okay, it's going to be real grouchy. All right, so I can do a less than symbol in there, and it can be kind of fun. So that's what happens when you put an inequality in there instead. So that's pretty nice, don't you think? Yeah, it is art. You could, suitable for framing. Look at that. And there's all kinds of really cool functions out there that I'll revisit this software later when we have a chance. But right now, I just wanted to give you a feel for the difference between explicit and implicit and make sure that you get it. Okay, so for now, we're going to consider explicit. Let's talk about domains. Now that you have a function of more than one variable, let's stick to an easy one, a function of two variables, which is typically given as z equals f of xy. The idea is it eats, if you will, it eats points, xy, points in the xy plane. So here's the xy plane here, and you feed it, any number of points here, and then the output is going to give you z, where z is some altitude. Okay, so the set D here, like let's say this is the domain, this, colored in oval, that would be the domain of the function, and the range would be the set of all real numbers z that get corresponded to each of the xy points. So here z is a real number, and the function is mapping you from 2D to 1D. It's a mapping, and if you took linear algebra, you'll know about transformations where you have a domain and a range, if you will, if it's a function, or a domain and a codomain if it isn't actually a function. I don't want to get too much into that, but you're linear, you'll have fun with that. Let's do a function machine now. So I like drawing function machines because it gives you kind of a more access to what you feed it and what the poo-poo is, the poo-poo being the range. So here's a picture of a function machine for us here. Function of two variables using that notation fx comma y. You feed this guy a point, x and y coordinates, okay, a point in R2, a point in R2. R2 is a fancy way of saying 2 dimensions. And the output is going to give you some z value, which is a real number. So let's do some evaluating of functions of two variables. Here's a nice function of two variables. Fxy equals 3x squared minus 2y. What if somebody said, hey, evaluate that at the point 3, 2? No problem. You're just going to substitute 3 for x, and you'll substitute 2 in place of the y, and the output is going to be some pure number. Let's see, 27 minus 4, I get 23 is the result. What if you were asked to evaluate at this point, -1, 4? No problem. The notation would look like f parentheses -1 comma 4. And again, you're just going to do some substituting. And you'll get some number here. What do I get here? -5. And that would be the z coordinate that gets associated with the x and y coordinates of -1, 4. What if you're asked to put a point 5 where the y is not determined? You can do that. You evaluate your function at 5y, so you're going to substitute 5 in place of x, and y will just stay y, and you'll get an expression in y. And you can do a similar thing for a point where the x is just, some arbitrary x, and when you evaluate your function at x2, you'll leave x alone. X is just x, and you'll substitute a 2 in place of y, and you'll get an expression in x. Okay, and then the last thing I'll do here for example 1 is this difference quotient is going to show up a lot in Calc 3. You'll see why next week. But what it's asking for is you're going to first evaluate your function f at x plus delta xy, that's some point, and then you'll subtract fxy, and then you'll divide by delta x. And it looks pretty gross, but here's the plan. The first thing where you're evaluating your function at a point x plus delta x comma, y just means everywhere you see an x, you're going to substitute x plus delta x. And everywhere you see a y, it'll just stay y. so you'll have 3, and then you'll have x plus delta x getting squared minus 2y. So there's the first term in this numerator. And then we'll subtract the original function fxy, which they gave us, which is 3x squared minus 2y. So I'm just substituting. And this is going to be all over some weird thing, delta x. And now you're just going to do a whole bunch of algebra. So this right here, you're going to want to expand and multiply, aka FOIL. So you guys probably are pretty familiar with foiling, right? First, outer, inner, last. So I'm just expanding it right now. I'm going to distribute this negative over the parentheses because I need to. And then I'm going to do a little bit of cleanup. Negative 2y added to 2y is 0. And then once I FOIL this mess, I'll have x squared, and then I'm going to combine like terms. I'll have 2x delta x terms plus the delta x getting squared, and then I have minus 3x squared all over delta x. And then you're going to want to distribute this 3 over the parentheses. So your numerator becomes 3x squared plus 6x delta x plus 3 delta x getting squared minus 3x squared all over delta x. Clean it up. We're still cleaning. Simplify. 3x squared minus 3x squared adds up to 0. So what do we have left? I still would not give you full credit if you left this as your answer. I'll give you some partial. You can actually simplify this a little further because the numerator has a common factor of delta x. Well, actually has a common factor of more than that, but let's just pull out the delta x. And then you can simplify this expression all the way. And so your final answer is this weird expression, 6x plus 3 delta x. And there's your answer to example 1. I know, pretty weird. Okay, I'm done doing evaluating. Next stop, let's find domains. Unlike the vector valued functions for finding domains, you don't need to find the intersection of sets where you have to, work a little bit to find that intersection, which gets a little bit crazy, which some of you found on the midterm a little bit. You still have to honor all of the issues that come up for domains. You still don't want to have 0 show up in your denominator. You don't want to take square roots or any even roots of a negative number, because we're trying to stay away from the complex number. And you don't want to take logarithms other than logarithms of positive values. See, those are still in place. Those are still in force when you're constructing the set for the domain. So take a look at letter A. One problem right now is, there's a variable in the denominator. Well, we do not want x to be equal to 0. So we'll write that down. And then we notice we have an even root here. And this even root appears in the numerator. So we need the radicand to be greater than or equal to 0. So I'm just going to rewrite this a little bit by adding 9 to both sides of the inequality. And we have all the restrictions now. We have 2 restrictions, and we don't write this in interval notation because you can't. We're not dealing with 1 dimension. We're dealing with 2 dimensions. We're dealing with the XY plane. So you're going to write your domain using set notation. What do you mean? You're going to use curly braces to indicate a set. The set of what? And then you got to do all the proper notation. Otherwise, I'm going to dock you points. Okay. You're going to put all arbitrary ordered pairs. So you're like the generic ordered pair looks like X, Y with parentheses, all the points. That means all the points. And then you're going to put a vertical bar here. That means such that. And then after the vertical bar, you're going to put any restrictions if you have any. And we've got 2 of them. X not equal to 0, comma, x squared plus y squared greater than or equal to 9. And this is the set notation telling us all the okay points that the function is allowed to eat. He's allowed to eat points, x, y, such that the x coordinate can never be 0 and that the x squared plus y squared has to be greater than or equal to 9. And we'll look at a picture of that in a moment, but let's do some couple of these other problems. Take a look at letter B. We got another function of 2 variables, which looks pretty gross. It's got a lot of terms in it. So we got a lot of issues we got to be careful about. The first term could have a denominator going to 0. That would be bad. So we don't want that denominator going to 0. And if I clean this equation up a little bit, or it's actually an inequality, but I'll pretend it's equals for now. We don't want y squared to equal 1/2. And if I square root both sides, and remember, anytime you square root both sides, and this is going to be key that you remember this in my class, because I'm going to test you for the rest of the semester. Anytime you take an even root of both sides of an equation, remember the plus or minus. So we don't want y to be plus or minus square root of 1/2. And that's one restriction. Are there any others? Sure, look at the second term. We have a logarithm. We do worry about logarithms because we always want the arguments to be strictly positive. So this is true, but I'm just going to rewrite it so it looks a little nicer. I'm going to rewrite it like that. And then the third term, we got to worry about, we don't want to take any even roots of negative numbers. So we need x to the 4th minus y to the 4th to be greater than or equal to 0. And then the last term has no restrictions because sine doesn't have any restrictions and xy doesn't have any denominators in it or any radicals or anything we need to be worried about. Now what? Well, now that you got all the pieces, put it all together. So the final answer for letter B, and boy, did I run out of room here, huh? The final answer for letter B using set notation, so you're going to have curly braces. You're going to say the set of all points, x, y, such that vertical bar. And by the way, some books, instead of a vertical bar, might have a colon instead. It depends on the notation that that book is using. I don't know what Briggs uses, but whether it's a colon or a bar, same thing. I prefer straight bar. That's just personal preference. Then you put all your restrictions in there, delimited by commas. So you go, okay, well, one of them was we don't ever want y to be plus or minus square root of 1/2, and then comma. And then we need x plus y to be less than 2. I'm just rewriting this inequality in the reverse manner. And then the last restriction is we need x to the 4th minus y to the 4th to be greater than or equal to 0. And that's the final answer for letter B. That's a lot of restrictions on his domain. I'm going to pause there. Any questions at this moment? Okay, before we do letter C, and I'll do that in a moment because that's, yeah.
Oh wait, no, I'm sorry. I thought that the letter, you had already done letter C because of the wording down there.
I'm not there yet. I know I go fast, Nathaniel, but I don't go that fast.
Sorry.
Yeah, no, we'll get to C. Hold on a minute. We'll get there. I want to just pause for a moment and let's graph letter A's answer. Let's go back to letter A. The answer was the set of all points with coordinates x, y, such that x can never be 0. And we need this inequality to be true, that x squared plus y squared always has to be greater than or equal to 9. What does that look like graphically in the xy plane? All the points that satisfy those conditions. Well, if x can never be 0, I hope you know that x equals 0 is the y-axis. You see how they have dotted lines right there, like doot, 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 on the y-axis? That means those dotted lines mean the points can never live on the y-axis. Those are forbidden. You're not allowed to feed this function any points where there's an x coordinate of 0. So that would obviously include this too. But the reason why they're not putting a dotted line inside the circle is because the other restriction where x squared plus y squared is greater than or equal to 9. First, let's graph x squared plus y squared equals 9. I hope you remember that that is a circle centered at the origin with radius 3. And because that's a greater than or equal to symbol, that border of the circle is a solid line. If it were a strictly greater than 9, then I would have used dotted line for the border of the circle, but it's greater than or equal to, so it includes the border of the circle. Any points that live on the border of the circle are okay for the domain. And then greater than or equal to means you shade in all of the points outside of the circle. So the function is allowed to eat any XY point. Come on, Microsoft Surface, you're letting me down here. Any points that live outside that circle, so long as they don't live on the y-axis. Remember, we have to also honor the other criteria, the other condition. So this is a picture of all the points that that function can eat. Pretty cool, huh? Now let's do the function of 3 variables. Now, folks, a function of 2 variables you can graph. Why? Because it's going to be a surface. So a surface you can graph in 3D. Unfortunately, a function of 3 variables, you cannot graph it. Well, why not? Because you need 4 dimensions. And I'm sorry, but we're kind of limited to being able to think about things in 3D because of, you know, the nature of the beast, okay? And don't come up to me after class and tell me, oh yeah, I can graph things in 4D. I'm not going to buy it, okay? Although our physics brethren try to, because when they're doing like string theory, they go, oh yeah, we're going to need 11 dimensions or 6 to whatever dimensions, and they start using these cubes where each cell of the cube is its own dimension. I've seen pictures of it. Don't even bring it up, okay? I don't want to go there. We don't graph anything that is more than a function of 2 variables. Function of 3 variables, you would need 4D to graph. Can't do it. But we can talk about functions of 3 variables. Certainly they are legit functions, and we use them to model things all the time. So what is this function of 3 variables domain? Well, notice we have a radical that's in the denominator, and this happened on the midterm, so I'd like to talk about it now. On the midterm, some of you kind of got tricked. I put a square root in the denominator. So some of you started off correctly. You went, oh, a professor told us that if we have a square root or any even root, you want the radicand, in this case 9 minus x squared minus y squared minus z squared, to be greater than or equal to 0. True. But here's the extra trick. Because this radical is sitting in a denominator, and you never want denominators to be equal to 0, this particular equation we need to, or inequality, we need to change to strictly greater than, because 0 isn't an okay option. And that was a little tricky on the midterm the other day. So remember that. And that's the only restriction for this guy's domain. So this guy's answer, let's do the answer for letter C down here. You're going to use set notation, so you're going to use those curly braces. But now you're going to have a point in 3D. So to represent points in 3D, we do use an ordered triple, all X, Y, Z points, such that vertical bar, and then you put the restriction. And in this case, I could write this, but if you don't mind, I'm going to rewrite that. If I add x squared plus y squared plus z squared to both sides of the inequality and then flip it around, it's going to look like x squared plus y squared plus z squared, strictly less than 9. And we're done. Now, what would that graph look like in 3D? Does anybody remember what that, if this were an equals, what this equation's graph would look like? I claim we studied it in the first week of this class.
It's a sphere with a radius of 3.
Yeah. Yeah, very good. You guys got it. Yeah, I can graph, you know, x squared plus y. It's a sphere. Good job. You guys remembered. Awesome. We've done so much in this class. It's amazing we can remember anything, right? But if I graph a sphere, oh, I know why it's not looking like a sphere. I have to do my parameters here. Oh, come on, dude. Give me the full sphere. Hang on a minute, I'll fix that. It's only graphing a portion of the sphere because I limited the x and y and z values. Okay, I think I changed it up so it should give me the full sphere now. Ah, there we go. And there's the full sphere of radius 3. And since it's implicit, I don't have all the color choices, but I can change it to solid colors. Ooh, pretty. Ooh, how about yellow? Oh, nice. Okay. Now, what if I change it to an inequality? You won't be able to see it because less than 9 means only the points strictly inside, so it can't graph those for you. But if I, so it's having trouble. It won't let me do it. Ah, too bad. But what it means for us is that our function of 3 variables can only eat points in space that are inside a sphere. So this less than means inside a sphere of radius 3, centered at the origin. Okay, so if you can imagine that sphere graph for you, all the points that live in the interior of that sphere centered at the origin, this function's allowed to eat. Pretty cool, huh? So here you can answer sphere centered at origin, and this dimension's required. I would put 4D. Radius 3 inside. So I'd say inside. Why can't you graph G? 4D. Can't be graphed. Can't graph it if it's 4D. Sorry. Okay, let's talk about graphs that we can do. You can always graph functions of 2 variables graphs, and that what they are surfaces. And I'm not going to ask you to graph all kinds of weird surfaces in my class, but I am going to ask that you understand basic surfaces and how they operate. Otherwise, the next 2 months are going to be no fun for you. And last semester, it was kind of tough because I had some students who could not get behind the basic idea, which is basically this page. And so when we got to integration, double and triple integrals, they just couldn't perform. And some of them had to leave the class, and that was sad. But, you know, you got to understand some of the basics first before you could do some of the high level. And if you think, well, I'll get away with not really understanding, I'm cool. And then it's going to bite you. So here we go. Graphs of functions in 2 variables. So the graph of a function of 2 variables is a set of all ordered triples for which this function, z equals f of xy, and the points that are in the domain. So here are the points in the domain. They're in 2D. You feed it a point here in 2D, and then it poops out an altitude for you. So the altitude, the z value, if you will, which is f of xy, gives you a point here. And so for each and every point down here in the xy plane, there's a corresponding point to it in heaven. Like this point right here has a point in heaven up here associated with it. This xy point down here has a point like this associated with it. And so when you connect all the points up here in heaven, you get a surface. Now, functions of 2 variables, if they are indeed a function, need to pass a vertical line test if they're really a function of 2 variables. So I hope you can see that this surface, if you just put a vertical line and passed a vertical line to the left and the right, it would only intersect that vertical line at most once at any given point in time. And that means it passes the vertical line test, just like the vertical line test you had back in pre-calc. Same thing. But this ellipsoid, even though it's a beautiful surface, and you guys have been introduced to ellipsoids when we did quadric surfaces, it doesn't pass the vertical line test. So it's not technically the graph of a function, because you see this vertical line here would intersect the ellipsoid twice. Now, this elliptic paraboloid, on the other hand, which is one of those cool quadric surfaces you guys studied a couple weeks back, it is the graph of a function because it does pass the vertical line test, because this vertical line here only intersects at most once. Okay. Now, although a surface doesn't represent a graph of a function like this ellipsoid, we can talk about it, you know, and do fun stuff with it. It doesn't mean, oh, we're not going to ever deal with it. Yeah, we'll still deal with it. It's still going to be around. Okay, let's do one example of finding ranges. Full disclosure, I'm not going to ask you too much to find ranges because it's a little bit tricky. It means you kind of have to have access to a good grapher. which there are some online like Geogebra. So I just want to mention, if you go Google up Geogebra, there's a 3D grapher there, and you can have fun and actually graph 3D stuff for yourself. You don't need my graphing software. The graphing software I use, the NewCalc, I believe is superior to Geogebra, just because sometimes I've noticed Geogebra can't handle every equation, whereas my software can. But you know, Geogebra does a pretty good job. Let's find ranges. So what about the output? What are all the possible z values that can get hit by this function? And it turns out that this function here, well, if you graphed it, it looks like this. It looks like the upper half of an ellipsoid. So you can just tell by looking at the graph that the lowest value of z that gets hit is z equals 0 in the xy plane. And the highest it hits looks like right there. That looks like the max z value there occurs at that point. So how would you get that? So it turns out when you're doing this kind of thing, the domain D has to still honor the fact that we don't want to get into a complex number. So you still need the radicand to be greater than or equal to 0. And if I write this inequality where I add 4x squared plus y squared to both sides, and then turn it into an equals, we want all the points that live inside an ellipse. Inside an ellipse. If I rewrote this ellipse equation where I got a 1 on this side, so I divide both sides by 4, it would be an ellipse centered at the origin with x-intercepts 2 and -2 and y-intercepts 4 and -4. Okay, so the range is going to be all values such that the z is above 0 or greater than or equal to, but less than or equal to the square root of what? Well, the biggest value that radical can get is square root of 16, because you're taking 16 and you're subtracting, ooh boy, didn't like that. You're subtracting something and then subtracting something else. So to make this number the biggest it can, you don't want to have anything subtracted. So 16 is the max you can get under the radical. So that would be square root of 16, which is z will go the full range between 0 and 4. And that's pretty much the answer. That is the range, or all the possible outputs for this function. So you're pretty much done there. So I'm just going to stop right there. Okay, and yeah, I hope you can tell by the figure. Okay, any questions so far? I'm not going to ask you to find ranges for the most part on quizzes or exams. Domains, yes. Domains, oh, absolutely. Ranges, not so much.
So basically the intersecting of lines, or rather not the intersecting of lines, the vertical line just is always meant.
A vertical line is just to help you determine if the surface is a function or not.
Okay.
That's all. Just to remind you, do you remember when you took, say, a pre-calc class or maybe a Calc 1 class where they gave you, you know, like
The 2D.
Yeah, 2D. You know, let's say they gave you some curves. Which one of these curves passes the vertical line test, Nathaniel?
The wavy one.
Yeah.
Not the spiral wavy one.
Yeah, but the spiral is still a cool graph, though, isn't it?
Yeah.
It's just not a function.
Yeah,
You
no,
can
it's
still
not.
talk about it. You can go, hey, this spiral is awesome. And what if I wanted to pick a point and draw a tangent line to it and find the equation of the tangent line? Just because it's not a function doesn't mean we, you know, throw it out the window. It's still fun, right?
Yeah.
So
Yeah.
you just use the vertical line to test if it's a function or not. That's all.
Okay.
Yeah, nothing special, just like you had in pre-calc. Let's talk about level curves now. So level curves, which is basically gonna wrap us up for today's talk, and then we're done, unless you guys want to talk about something else. And if we have extra time, if you want to look at midterm solutions, that'd be okay with me. But Has anybody here heard of contour maps? I don't know if you've heard of contour maps.
Yeah.
Maybe, maybe not, or maybe a topographic map. You know, when you look at a map and you see all these wavy, squiggly lines on it, that's a contour map. What does it mean? Well, it kind of gives you an idea of elevation when things are not as high, you know, when sea level or, you know, whatever. You'll notice that over here, the little squiggly lines are not as close together. What does that mean when they're spaced apart so much? It means
It's
the elevation changes slowly, right?
yeah, like it's less.
Yeah, so like if you were hiking, and I've been doing hiking these days since the pandemic hit and my gym is not open. When I go hiking, sometimes I like, you know, if I'm lazy, I don't want to have a lot of hills, you know, or mountainous ranges. So if I'm lazy, I'd hike, you know, in areas where the contour map shows widely spaced. So, you know, I don't have to like, you know, work so hard. I don't want to have to work the glutes. On the other hand, if I'm feeling like today, me and my husband are going to do a hike down this canyon that's outside my house, and there's some serious inclines there. Okay, I mean, it's gonna. I'm kind of looking forward to it because it's nice fresh air. On the other hand, my glutes are already crying because they're like, oh, it's gonna hurt because these mountainous ranges have these contour squiggles real close together because it's rapidly changing incline. Ouch! But it's good for you. Good for your physical fitness. Okay, so here's a little picture to help sort of get more of the idea. If you look at this little mountain, here's one contour curve. So how would you get a contour curve? The way I like to think about it is if you were flying overhead here in a plane and you were looking straight down, what would those curves look like? Those contour maps are two-dimensional, even though they're basically corresponding to a 3D surface. So if
Isn't
you
it a
look,
bunch of circles?
yeah, for this one, it would be a bunch of circles. So this would be the contour map that, or they also call these level curves for a reason, because if you look at one of these curves, if you were a hiker and you just walked around the mountain around this path here, you would never change altitude. And that's why they call it a level curve. If you kept walking around that circle. So if you stayed on any one of these level curves here, you would never change altitude. The minute you leave your level curve, like let's say you were on this level curve here, and you jumped down to the next level curve, you would be changing your elevation, your altitude. Okay, so here's another picture. Check out this, I don't know what that would look like. That looks like two skinny mountains. The level curves and the contour map for that guy looks like that. Interesting. Kind of fun. Okay, so these are just some basic pictures. So let's do one. How would you get to figure out the level curves and the contour maps for a given function? So I'm going to show you how to go through this step by step. Okay, you're going to have this on my math lab. Face to face, I don't give you multiple choice, although typically my math lab is really nice and gives you multiple choice graphs. So, but you have to pick the right one to get your credit. So you're going to have this on quiz 4 this Sunday. So they'll give you some function of two variables, and then they'll go, okay, what's the contour map for this guy look like? And then they'll give you some multiple choice choices. So you got to pick the right one. So I hope you can see that it does look like it's going to be a bunch of concentric circles, but how did they get that? Because you would have to figure that out. So step 1, and if I don't see step 1 on your paper, even if you picked the right answer on your multiple choice, I take away points. Step 1 is you're going to set your function equal to a constant. Why? Because a level curve is essentially where you're basically graphing the function equal to some constant c, because this now becomes a 2D curve once you set the function equal to a set level altitude. Then what? Actually set the function equal to a constant. And then step 2 is rework this equation just using some algebra to see what the equation reminds you of. Because right now it doesn't look like anything that I remind you of what. If I square both sides of this equation and then I rewrite it where I get the x squared and y squared terms on one side and the constant term on the other, I claim this, this equation looks like the standard equation for a circle centered at the origin with radius what? Well, the square root of whatever 64 minus c squared is. The square root of that funky number that you see on the left-hand side there. So the question is, what is that funky number? I mean, you want to pick some nice numbers. Like if I let c equal 0, then the level curve is going to be really easy to graph because it'll be the equations graph x squared plus y squared equals 64. Ooh, that's a terrible looking circle, but I think you get. So that's one of the level curves right there. And if I let's try another one. What if I let c equal 7? Okay, so then I'd have 64 minus 7 squared equals x squared plus y squared. What the heck is 64 minus 49? I don't know, 15? So this is going to be a circle with radius square root of 15, which is a little less than 4. Okay, so here's the 4. So that level curve would look kind of like that. Okay, and you could do some more values of c and then keep going, although you want to probably limit it to no more than c being 8, because then you'll get a negative radius and that's impossible to graph. But you'll get a collection of circles. So that makes sense. Like if I do c equals 8, I just get a dot and, you know, different values of c. So you're going to get a bunch of concentric circles. So we're done with that. And not too hard. Yeah. Now, what about a different surface? What about this puppy? Well, what does that even look like? Well, you may not have access, or you don't maybe want to go graph, you know, something. You don't need to know what the graph looks like to get the level curves. So I'm going to do this in reverse. I'm going to first get the level curves, and then I'll go and graph it. Okay. So without even knowing what this surface looks like, let's just go get his level curves. So step 1, I want to see it. Set the function equal to a constant. What do you mean? Set y squared minus x squared equal to a constant. Then what? What does this remind you of? Like, I don't know. If you'll recall from your pre-calculus days that y squared over b squared minus x squared over a squared equals 1 is a hyperbola. In fact, it's one of those up-down hyperbolas. So, you know, it looks something like this. You guys remember that? Where the b and negative b are the y-intercepts. Hello?
Yes.
So if you let c equal 1, this is an easy hyperbola. It'll just be an up-down hyperbola where 1 and negative 1 are the y-intercepts, and it doesn't have any x-intercepts. Now, what if I let c equal negative 1? Watch what happens when I let c equal negative 1. C could be negative. C equals negative 1. We have y squared minus x squared equals negative 1. Now, the standard equation for a hyperbola centered at the origin, you always want to have a positive 1 on the right-hand side. That was the typical. So if I multiply both sides of this equation by negative 1 so that I get the right-hand side having that positive 1, then this hyperbola equation looks like this. Let me rewrite it, where it flipped. The x squared is now positive and the y squared is negative. So that's a hyperbola that what we call one of those left-right hyperbolas, where it's got x and intercepts, negative 1 and 1, but no y-intercepts. Ooh, that's weird. So it's going to turn out for positive C values, you'll get up-down hyperbolas. And if you substitute negative values for C, you'll get a collection or a family of left-right hyperbolas. So this is what the contour map looks like for this surface. Pretty cool, huh?
Yes.
I don't know if you, maybe you don't think it's cool. I don't know. Here is something I wanted to show you. It's a different problem. Like, look at this surface that looks kind of like a wavy potato chip or something. And they're looking at some of the level curves there in the middle. So if I hit play here, and the level curves start changing depending on which level you're at. You see that? And the corresponding contour map is on the left-hand side. So cool beans, huh?
Waves.
So they're just giving you the different level curves for this particular interesting surface. So that's kind of neat. I like that. So, okay, that was fun. Now what? I want you to see how to get to Geogebra. So if you go Geogebra, and then you notice one of the choices is 3D, yay. And you're like, oh, what's that? You know, and then you just go, okay, go to the www.geogebra.org, and you're like, okay, now what? Because if you're interested in looking at some of these, let's see if I start calculator. I haven't used this for a while, so let's see if I can screw this up pretty well. How good can I screw this up? I don't know. It looks like, there we go. So if I type in z equals, and then this, we were working on this example 5, y squared minus x squared. Oops, I screwed up. Sorry, I got to go down. Oops, sorry. Come on, baby. There we go. Minus x squared. And then try and graph this. Let's see what happens when I hit return. Will it graph it? Nope. Let's see about settings. Does that help me? Show object. Color. I don't know. Let's do yellow. Okay, hit it. Doesn't look like it wants to graph it. Oh, yeah, that's too bad. Well, I don't know why this isn't working, but I don't have time to sit here and futz around with it. It looks like it's not happy, but it also looks like I'm not in 3D. So let me just see something here. If I have to do something else. Nope. Let me get out of here. .3D calculator. I don't know why my internet's really slow. I've had some internet issues. There we go. This looks like the better place to be. So maybe this is why it was unhappy. Don't know. So if I'm graphing the y squared minus x squared function, whoa, what just happened? So you'll notice, whoa, that is one funky looking surface here. And it's kind of, I don't know how to back out here, but it basically looks like a horse's saddle, which is really hard to see here. Let's see if I change colors. Settings. Let's do that. Ooh, nice. Okay. I wonder if I could zoom out. Can I? No. Maybe I could zoom out. Zoom out. Zoom out some more. No. Okay. It's kind of hard to see. So this is GeoGebra. It helps you see some stuff. I'm not real happy with it. I like to go back to mine. I'm sorry. I like mine better. I think it does a better job. Okay, so if I graph on my software, yay, let's see. It's a little bit better. So I can also rotate it, which is kind of fun. I hope you can see it kind of looks like in a sense, it looks like a horse's saddle. Like if I zoom in on it. You can kind of see it looks somewhat like a horse's saddle. Kind of cool. Anyway. And, you know, of course, since this is explicit, I could do different colors. Ooh, yeah, baby. That looks pretty exciting. Doesn't that surface look cool? How about stripes? Ooh, that looks cool. How about rainbow? How about bars? Ooh, nice. Candy stripes? Trippy. Okay, enough fun for now. All right, so basically you get an idea of the surface, but the question is, looking at that surface, can you get that their level curves look like all of these hyperbolas if you were looking straight down on it? Would you be able to picture that? Maybe not as easy.
Yeah.
But those hyperbolas correspond to this surface, folks. I'm just saying. That's the contour map for this horse's saddle. Ah, nice. Love it. Okay. So I'm done doing level curves. Congratulations, you're now done with level curves. And you'll get to have some fun doing them on your own with the homework. It's not that bad. You know, there's no calculus involved. You don't have to take any limits or derivatives or integrals. You know, we're just doing an introduction right now to functions of more than one variable. That's all. So we'll finish today with level surfaces. So what's a level surface? Well, if you have a function of 3 variables, which you can't graph, you can look at its level surfaces. So just like you have a function of 2 variables, which you graph in 3D, and his level curves drop you down by 1 dimension, the level curves that correspond to a 3D surface are 2-dimensional. When you have a function of 3 variables, which would require 4 dimensions to graph, forget it. But the level surfaces that apply drops you down 1 dimension to 3, which you can look at. So the level surfaces for a function of 3 variables you can look at. So how do you do that? Step 1 is going to be set your function equal to a constant, and then examine the equation, and does it remind you of something that you already know the equation for? Maybe it's a quadric surface or whatever. So let's take a look at one example here. This function right here, f of x, y, z equals 4x squared plus y squared plus z squared. You cannot graph this. You would need 4 dimensions to graph it. So I can't graph it. But you can still talk about functions of 3 variables. It's not a problem to talk about it. Now, the domain of a function of 3 variables lives in space. So it's some ordered triple that you feed this function of 3 variables, and it poops out some number that corresponds. So, well, I do want to give you one relevant application. Say you had a room. Let's say, you know, the room you're sitting in now. You know, I don't know what the room you're sitting in now looks like, but let's say it looks like this, you know. And so this represents space. And if you pick a point anywhere in your room, let's say like you're right here, this point x, y, z, and you evaluate your function at that point, it's going to give you some number. So what's an application? What if this function were what we call a temperature function? That would give you the sum number would be the temperature at that particular point in your room. And that is a really great application for a function of 3 variables. You feed it a point in your room in space, and it outputs a temperature corresponding to that point. So you could feed it different points in your room, and you would get different temperatures corresponding to different points in your room. Yeah, so that's an application. So let's look at level surfaces. So in your room, say, there might be like a surface here that if you at least stay on this sphere in your room, you would stay at the temperature, I'm just making something up, 65 degrees Fahrenheit. And if you moved off of that sphere, maybe you would then start heating up or cooling off or whatever. So you could have this idea of a level surface. So how would you figure out the level surfaces for this function? Well, once again, you're going to set your function equal to a constant. That's always step 1. So for us, we're going to set 4x squared plus y squared plus z squared equal to a constant, and that will give us a level temperature, or a level surface. And folks, I claim that this equation should be somewhat familiar to you because it's the equation of an ellipsoid. And so the answer is the level surfaces for this function of 3 variables will just be a collection of ellipsoids. That's it. That's all we're going to do for that lovely example. And let's move on. Okay. And I talk about this residing in 4 dimensions. Okay. Now, for those of you who are going to take higher levels of math, you are going to run into functions of more than 3 variables, maybe 4, 5, 6, 7, 8, 9, 10, 100. And you may be thinking, well, that has no relevance to real life. Sure it does. If somebody wanted to model, say, the United States economy, that might be a function, if you will, of many variables, like the unemployment rate, tax rate, number of people that live in the country at this time. You know, all sorts of factors would come into that model, and you would maybe have to worry about 100 different things, 100 different variables for that function. Absolutely, that could happen. So this idea of a function of more than one variable, x1, x2, x3, and so on, as long as you delimit them by commas, this would be the notation for your function. Now, this x to the n plus 1 is typical. So you guys know when you have a function f of x, it's okay to rename that y. That's very typical. So similarly, when you have a function like of 2 variables, x, y, typically you'll rename it some other letter, z. So z can replace fxy. Just like when you were in math class and somebody said, well, y equals x squared. You could go, yeah, but y means the same as f of x. And so these were equivalent, right? Please say yes when you took algebra, right?
Yes.
Okay. So similarly, if somebody gives you, oh, fxy is equal to x squared plus y squared, don't worry about this step right here where you replace your fxy with z. That's pretty standard. So similarly, like if you had a function of 3 variables, x, y, z, a lot of times they replace it with a single letter. For example, w is pretty common. So this f, x1, x2, x3, you know, all however many n variables that it's a function of, you could replace it with some other letter to make it less awkward. Okay, so the domain is going to be the set of all ordered whatever n tuples, they call this an n tuple, that would be okay for that function to eat. Like you want to maintain an integrity where you wouldn't want to make denominators go to 0 or anything like that. Okay, so here they're just showing you a chart. I love this chart because it just sort of gives you access to all, you know, the different possibilities out there. And when you take linear algebra, oftentimes you work in more than 2 or 3 dimensions. Sometimes you work in n-dimensional space. And so you need to be able to think outside the box, and your brain has to be able to say, okay, n dimensions are okay. So here's a function of 1 variable, and you did that in Calc 1. And here's when you rewrite it and you get everything on one side and 0 on the other, and then you rename the junk on the left-hand side big fxy, because this is now considered a function of 2 variables, because it's got x's and y's in it now. And when you rewrote it where you got everything on one side and 0 on the other, that's considered implicit form. And we're going to need that in about a week or 2. So don't lose sight of that. You're going to need to move it out and get everything on one side and 0 on the other. It's going to happen. And then if we just learned about functions of 2 and 3 variables, and you can talk about the implicit format of it. So for functions of 1 variable, like you did in Calc 1, you only needed the xy plane to graph it. But now when you have a function of 2 variables, you need 3D, or what we call R3. You need XYZ space. And for a function of 3 variables, you would need 4 dimensions to graph it. Forget about it. You're not going to graph it, but you can talk about R4. And for a function of n variables, you would need n plus 1 space to graph it. So don't even think about graphing it. But hey, it could happen. But this is a nice summary for all the possibilities of functions of more than 1 variable, for sure. So I'm officially done with today's lecture, but look, if you want to stick around to get questions answered,